All right, this unit is on circuits and using Kirchhoff's laws to study circuits that have more than one resistor hooked up in series or parallel or some combination of series and parallel. The lesson is broken into two mini lessons. The first one will focus on looking at circuits that have more than one resistor in them. They can be hooked up in series or parallel. And the second mini lesson will focus on actually using Kirchhoff's laws to make sense of more complicated circuits. All the images that you see in this video are attributed to OpenStax College Physics, distributed under the Creative Commons Attribution License version 4.0 by openstax.org. All right, let's take a look at this circuit up here. It's composed of a battery connected to three different resistors, R1, R2, and R3. And these resistors are hooked up in series. What I mean by that is each experiences the same current. The same current flows through all three. There's only one path around this circuit from positive to negative on the battery, and that path takes you through all three resistors. So they're hooked up in series. Now, when resistors are in series like this, what we can do is we can recast the circuit as some other circuit that has an equivalent total resistance, which is reflects a combination of all three resistors, in this case R1, R2, and R3. And the rule for combining resistors in series is that they simply add together. So in this case we have three resistors, so they add together to give you the total equivalent resistance of the circuit. And so this three resistor circuit can be recast as a one resistor circuit where the resistance of that resistor is equal to R1 plus R2 plus R3. If you have more than three resistors, the rule extends. If you have four, you just add R1, R2, R3, and R4 together, etc. So in series, resistors add together, and the combined resistance is always greater than any of the individual resistors. Now, this second circuit right here shows three resistors, R1, R2, and R3 in parallel. They're hooked up in parallel. That means you can trace a path from positive to negative terminal in the battery that goes through R1 or R2 or R3 independently without going through the other two. Another way of saying that is R1, R2, and R3 experience different currents because they're on different branches of this circuit. So when you have resistors in parallel like this, the equivalent resistance is actually diminished. It's less than any of the individual resistors. And the way you figure out the equivalent resistance is by using this rule, where the reciprocal of the resistances add together to give you the reciprocal of the total resistance in parallel. And again, this rule extends if you have 4 or 5 or 6 or 2 resistors in parallel. The same rule applies, just with more terms. All right, well, here's a more complicated example. We start with this circuit up here, and this circuit has a total of 7 resistors. And it's not simply a parallel arrangement or a series arrangement of resistors, it's a hybrid. So what you got to do is you got to zero in on specific parts of the circuit and combine the resistors in that part of the circuit following the rules on the previous slide, and go to sequentially simpler and simpler arrangements of equivalent resistors in this circuit. So for example, these three resistors right here are in parallel, so we can use the rule for combining parallel resistors to figure out the equivalent resistance of those three resistors in parallel, Rp, and we can plug it in over there. We can replace those three resistors with one resistor that has an equivalent resistance to the three combined. And the same goes for here. R5 and R6 are in parallel. They combine to give you Rp prime. So replace those two resistors with Rp prime in the circuit. All right, well now these equivalent resistors that came from over here, Rp and Rp prime, are now in series with one another. They're both on the same wire, the same current flows through both, so I can use the rule for combining resistors in series to combine those two resistors together to give me Rs. and I replaced the two resistors with RS in the circuit. Now, in this equivalent circuit, RS and R7 are in parallel with one another, and they're on separate branches of the circuit, so they can be combined to give me an equivalent resistance RP double prime using the rule for combining resistors in parallel. And that gives me this equivalent circuit, where now I only have is R1 and this combined resistance of R7 and RS, RP double prime. And those two resistors are in series, so they can be combined by adding them together to give you one final total equivalent resistance RS prime. And we've simplified this 7 resistor circuit to an equivalent circuit that has a single equivalent resistance for all the resistors combined together. Okay, so this is the last slide in this mini lesson. And the point of this slide is to emphasize that voltages simplified or signified by a symbol like this in our circuit diagrams can be supplied by batteries. And batteries are imperfect devices. So batteries supply a voltage, or something that's also referred to as an EMF, for electromotive force. For our purposes, let's say that EMF, or electromotive force, which is oftentimes abbreviated E, is the same thing as a voltage. It has units of volts. All right, but batteries are devices that supply this voltage or EMF, but they're also devices that are imperfectly designed, so they have some measure of internal resistance, represented by little r here. So a more accurate way to look at a circuit that is supplied a voltage by a battery is to think of the battery as an arrangement of an EMF, a voltage, and a small resistance, a small resistor R. And the advantage of thinking about this way is we can see then that as the current being driven by the battery increases, the amount of voltage, remember Ohm's law, V equals I times R, the amount of voltage that's going to be consumed by the internal resistance of the battery will also increase. So in general, as the current goes up, the amount of voltage that's left over to be supplied to the external circuit decreases, because proportionally more of the voltage gets consumed by the internal resistance of the battery itself. Okay, so this concludes mini lesson 1. The next mini lesson in this circuits and Kirchhoff's law unit will focus in on Kirchhoff's law and how they can be used to uncover the function of more complicated circuits.